A2 Further Maths, Group Theory. Okay, so we've got a set here. The set consists of the numbers 1, 2, 3 and 4. And what I'd like you to do is construct a Cayley table so that you can take any of those numbers, 1, 2, 3 and 4, multiply them by another one of those numbers, 1, 2, 3, 4, under the multiplication modulo 5. So there's a binary operation. Any of those numbers multiplied by any of those numbers, and don't forget the result is modulo 5. So just have a go at producing the Cayley table to show all the possible results for that. Okay, just pause there then, have a go. Okay, so from the Cayley table, hopefully what you've done is you've put the set 1, 2, 3, 4 and the set 1, 2, 3, 4 down the side, and we're looking to multiply those two numbers together. So it's not difficult with the multiplication. 1 times 1 is 1, 1 times 2 is 2, but you need to be careful. 1 times 3 is 3, 1 times 4 is 4, fine. When it comes to the 2 times tables, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, but do not forget that we're dealing with modulo 5. So the number 6 would actually go back to the number 1. Okay, because 5 is equivalent to 0, so 6 is back to 1. Alright, remember what it's doing it is take off the modulo from it, or any multiples of the modulo, and the number you're left with, when you can't take up any more, is the answer you're looking for. So 2 times 3 is 6, 6 take away 5 is 1. 2 times 4 is 8, 8 take away 5 is 3. So 8 would be 3 in modulo 5. Right, so if you've forgotten that, just have a go at filling out the last two rows. Okay, so what did you get? 3 times 1 is 3, 3 times 2 is 6, which is obviously modulo 1 again. 3 times 3 is 9, 9 minus 5 is 4. 3 times 4 is going to be 2. Alright, because you've got 12. So 3 times 4 is 12, take away 2 lots of number 5, literally 2. 4 times 1 is 4, 4 times 2 is 8, that's okay, that's 3. 4 times 3 is 12, we just did that one's 2. 4 times 4 is 16, so that's the same as taking away 5, take away 5 again, that's going to get you 6, take away another 5 would get you 1. Okay, so there we go, I've filled up my Cayley table for the set 1, 2, 3, 4 under the binary operation of multiplication modulo 5. That's my first question. Is the binary operation associative? So have a think about it, see if you remember what associative is. Okay, so associative means, does it matter if you pick any 3 of the numbers, and it could be the same number twice. So let's take the numbers 1, 2 and 3. If I did 1 and 2, get a result and then times it by 3, is that exactly the same as doing 2 and 3 first and multiplying it by 1 afterwards? Does it make any difference about the order? If you do 1 and 2 first and then 3 to that answer, do you get exactly the same as if you do 2 times 3 and then times by 1 second? Now multiplication is associative. It doesn't matter that it's under modulo 5. Alright, multiplication is always associative in this situation. So therefore, we know these two things are associative. Alright, so it's associative. Have a think about that. What's the identity element? So you need to go back to your binary operations, consider what the identity element is. You might want to check in your notes. Okay, so an identity element is anything that works like this. If you do the identity element times by any given number, you always end up with that given number. But it's also true the other way around. If you take the number and you multiply it by the identity element, you always end up with the same number. All right, that times sign here, in this case, is because we're doing multiplication, but that could be any of the binary operations. You should be careful because sometimes there isn't an identity, a unique number. So in this case, E times A, I would say number 1 is going to be the identity element, because 1 times 1 is 1, 1 times 2 is 2, and so on. Alright, so if 1 is there, then the answer is always going to be A, and if 1 is there, the answer would always be A. So therefore, I would say yes, it has got an identity element, the identity element is 1. Okay, think about this question. Each element in the set S has an inverse element that is also in the set S. Okay, think about what that inverse element is. Okay, so if you've got what an inverse element is anything like this. Can you, if for any given number in there, can you times it by any other number so you end up back at the identity element? Now, if this was just general multiplication, then it has to be in all the numbers like this. 2 times a half would be its inverse element equals the identity. All right, but we're not dealing with halves or anything like that, but it still could be true in the binary operation. So take the number 2, for example. 2 times what number would get you back to the identity element 1? Now, of course, once you're at 2, you might be thinking, well, it's 2 times a half, isn't it? That's 1. No, not in this case, because you're looking at modulo 5. So 2 times 3 could work. If I did 2 times 3, the answer would be 6, but 6 is the same as 1. And I think it's true that every single element, 1 of course is definitely 1, because 1 is times 1. 2 could be times by 3, and that would definitely get you the answer as 1, because 2 times 3 is 6, modulus 5 is back to 1. 3 is times by 2, so that's okay. And 4 would be times by itself. 4 times 4 is 16, and 16 is number 1 in modulo 5. So for every single element in this group, there is an inverse element that takes you back to the identity. Right, so we're showing it's associative, we're showing it's got an identity in the group, and we're showing that it's got an inverse element for every single one of our elements. Now all those rules are important. Pick any 2 elements in the set S. Doesn't matter which ones they are. Okay, any 2 elements in the set S. If you perform the binary operations on those elements, you get the answer as 2. The result you get is always in the original set. It doesn't matter which 2 numbers you pick. Right? I just randomly picked 3 and 4. Whatever numbers you pick, you'll notice that when you multiply under modulo 5, an answer you get is always in the original set. Now that means that the actual set itself is closed. If the result you get from the binary operation always gets your result that's in the original, then the set is closed. Now that wouldn't have been true for addition, for example. All right, if I did this addition, 1 plus 4 is 5, but 5 in modulo 5 is 0, and notice that 0 is not in the original set. Okay, so it's not always true. It's only worked, or it does work in this case for multiplication, but for addition it would be very, very different. Okay, but in this case this set is closed because whatever answer I get from any of these is always in the original set 1, 2, 3, 4. And it's pretty obvious. You can see all the answers in the Cayley table are answers 1, 2, 3, and 4. There's nothing else in there that wasn't in the original set. Okay, so it's definitely closed. Now, because it fills out those criteria, all right, it meets these conditions. It's definitely closed. All right, all the results we got are definitely in the original set, so it's definitely closed. It's associative. It doesn't matter about the order. All right, take any number, times it by any other number, then times it by a third one. Could have been done the other way around, and it would still be the same answer. Okay, so it's associative. It contains the identity. All right, so the group contains the identity. That's important. And each result has an inverse, which is also in the result. So that bit's important. Okay, so it's not just a case of all these numbers have an inverse, is the number that's its inverse also belong to that set. Okay, now because those 4 conditions have been met, it's closed, it's associative, it's got an identity, and each result has got an inverse, then you would say that that group, so that set under that operation forms what we call a group. Right, as long as it fills out those 4 conditions, that set under that binary operation is what we call a group. Okay, so if we took a set of numbers and we performed the binary operation, circle with a cross in it. So we performed this binary operation on that set of numbers. The answers we get out form a new set, the set G. Okay, so the set G is formed under a binary operation. Right? If it satisfies these four axioms, so if this new set that we just formed satisfies these four axioms. Now, an axiom is a rule that's just accepted as true. Right? You don't need to prove it, it's just accepted as true. So these four axioms, you don't need to write that bit down in your notebook, is this. The first axiom is that G is closed. Now, what we mean by G is closed is that every single element in G, all right, every single element in G, when you do the operation to any two elements in G, and it could be the same element, it doesn't matter which ones they are, so A and B could be the same. So any two elements in G, under the binary operation, what you end up with is a result that's also in G. You never get an answer that's outside of G. Okay? So if that's true, then G is what we call a closed set. G is closed. So any two elements, do the binary operation, the answer you get out is also in G. It's a closed set. If G is associative, in other words, you take the binary operation and you do it in either of these two orders, they are exactly the same result. All right? You've seen examples of this with matrices where it's not associative. Of course, matrices or subtraction. All right? Subtraction's not associative, or division, as you know. So not everything's associative. But if it is associative, and for all the elements in G, right, it's not just one set of group numbers, but for all numbers in G, or all elements in G, then you can call it associative. So as long as it's closed, as long as it's associative. There's an identity. In other words, there should be some number within the group that basically, if you take that number and multiply by any of the other numbers in the group, or not multiply, but do this binary operation to any other numbers in the group, you always end up back with the original number. All right, so take the number, do the binary operation to this, whatever the identity is. It's exactly the same as doing it the other way around. All right, what we call commutative, it doesn't make any difference, equals the original number. So a really simple example, if a multiplication, it would be 1. Any number multiplied by 1 is equal to the number itself. 1 multiplied by a number is equal to the number itself. If it's addition, it would be 0. Any number plus 0 is equal to 0 plus any number, which is always the number itself. If it's matrices, of course, it's the identity matrix, 1, 0, 0, 1. So there's lots of different identities out there. Right? It's not always obvious, though. It's very easy to spot from a Cayley table, though. So as long as it's got an identity within it, if it doesn't have an identity within the group, so if it is multiplication and number 1's not in it, if number 1 is the identity matrix, identity element, if 1's not in the group, then it's not, it doesn't satisfy that axiom. And the last one is the inverse. So take any two numbers within the group, okay, any two numbers in the group, and they must fulfill this bit just here. All right, so if you've got a number in the group and the element in the group, because you've ticked that box, there must be another number or another element within the group, or within the set, I should say, so that A binary operation B is exactly the same as B binary operation A, which is exactly the same as the identity. Okay, each number should have an inverse within the set itself. Now, for each of those, if they are satisfied, then that set G that's formed under the binary operation can be called a group. Okay, as long as it satisfies the closed associative, identity, and inverse, then you can say that that set G is called a group. Okay, just pause there, take down what you need. Okay, so let's have a look at a slightly different Cayley table. I've set it up for you. Can you have a go at filling that Cayley table in, please? 0 to 5, as you can see, there's a set, and addition modulo 6. All right, so have a go at filling that in. Just pause there, do it yourself. Okay, so let's see. 0 plus 0 is 0, 0 plus 1 is 1, so on and so on. Just be careful when you get to 1 plus 5 is 6, but that's back to 0. Now, as you can see it's going to be close because every single answer within this Cayley table here is within the original bit. So we know it's closed. Closed is fairly easy to spot. Okay, but I want to know, does it fill out the other axioms? So therefore to tell me whether G is a group or not. All right, so have a go, have a think about it. Okay, it's definitely closed. We just mentioned that. So all the answers we have in here definitely belongs to the original set. Is it associative? Right? Is G associative? Yes, it is. 1 plus 2 plus 3 is exactly the same as doing 2 plus 3 plus 1. It's exactly the same. Addition is associative. Okay. Does it have an identity element? Yes. 0. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2, and so on. Okay, so 0 is the identity element. All right, definitely ticked off. And then finally, you take any number in there. Could you add another number within the set so you get back to the identity element? So there we go, 4. All right. If I want to get back to the element, I need to add 2 to that to get to 6, and 2 is within the real group, within the original set. So therefore, I can pick any number and do that. 3. 3 plus itself. So 3 plus 3 is 6. 6 is the same as 0. So you take any number, you can add something else to it to get back to 0. All right, so every single one. So therefore, because it fills out all these criteria, right, closed, associative, identity, inverse, then you can say that this group, G, is definitely a group. Right, G is definitely a group. And you need to be in a situation to be able to spot whether a given set under a certain binary operation forms a group or doesn't. Okay, let's look at another example, but this time a slightly more basic example. All right, set 1, 2, and 3, same situation, addition modulo 6. All right, forms this new set. We're going to call it set A. So this is going to form this new set just here. What's this new set look like? All right, and is this new set a group? So is A a group? Well, have a look. I think you can spot it almost straight away, or you should look at spotting it straight away. And noticing it's not a group. And the reason why it's not a group, you need to be able to say it. It's got the identity in there. Right? I think it's got the inverse in there as well, because you've got any number plus any number gets you 0. 4 plus 2, 3 plus 3, 5 plus 1, 0 plus 0. So everything's got an inverse. Okay, it's associative, yes, but it's not closed. It's not closed because if you look, you've got 2 plus 3. 2 plus 3 is 5. Now 5 was not in the original set, so therefore it is not closed. All right, so you're looking for that pattern. 5 is not within the set S. A is not closed, therefore A is not a group. Okay, that is not a group in that situation. All right, so you need to be careful. You need to be thinking about all the different rules. You're looking for one that fails, therefore it's not a group. Okay, let's do the same thing, but this time just with different numbers, 0, 2, and 4. Try that. Okay, fill it in and answer the same question. Is B a group? Okay, so let's go through the checks. This one's a little bit more unusual, isn't it? All right, is B a group? Well, all the elements in that answer, in that set there, in the set B, all right, were in the original set S, weren't they? 0, 2, 4, 0, 2. All of those answers were in this original set 0, 2, 4. So it's definitely closed. Right? It's definitely closed. We don't have some unusual number coming out that wasn't in the original set. All right, so B is definitely closed. Also, B is associative. 0 plus 2 plus 4 is the same as 2 plus 4 plus 0. It's exactly the same for every single one of the values. All right, addition is, you could just write addition is associative. It contains the identity. That's important. It does contain the identity element 0, so therefore that's okay. All right. And finally, you take any number in there, you take any number in there, can you add one of the other numbers in there to get back to 0, because 0 is the identity? Well, 0 plus 0 is 0. 2 plus 4 is 6, which is 0, so that's fine. And 4 plus 2 is 6, which is 0. So I would say that all the values have an inverse. So therefore, I would say that B is a group. Okay, so there's nothing wrong with reducing it down. There's nothing wrong with having it smaller, all right, compared to the original group. 0, 2, 4 is smaller than the original group. All right, 0, 1, 2, 3, 4, I think it was 5, wasn't it? There's nothing wrong with reducing it down as long as it still follows through with each of the 4 axioms. Okay, if you actually have a look at these two we just done then. So the group A didn't work. Right? The group A was that group just there. It didn't work. It wasn't a group. I shouldn't say group A. It was a set A of these results, but it didn't form a group because 5 was not in the original. But this group, this was a group, group B, 0, 2, 4, definitely did work. Now notice that 0, 2, 4 is actually within this original set. In fact, it was a subset. All right, 0, 2, 4 is a subset of S, isn't it? 0, 2, 4. Okay, and we notice that because it's a subset and it's also a group, then B is called a subgroup of G. All right, so not all subsets are subgroups. We saw 0, 1, 2, 3 failed to make a group. Right, 0, 1, 2, 3 failed to make a group. So 0, 1, 2, 3 was not a subgroup of G. But 0, 2, 4 did succeed in making a group. We can still see it there. So therefore B is a subgroup of G. So if your subset is also a group and the original set was a group, then you can say B is a subgroup of G. Okay, but it's absolutely vital you understand that B has to be a group as well. I'd like you to see if you can find 3 sets. What other 3 sets would also form a subgroup of G? Okay, so just pause there. Do have a go at yourself, have a think. Can you think about which 3 sets would also form a subgroup of G? You might just get 1 or 2, just try. Okay, so let's see how far you got then. So 0 and 3, did you spot that one? Okay, that 0 and 3 gets the results 0 and 3. It's closed, it's got an identity, 0. It's definitely associative. There's nothing wrong with that. Even though there's 3 numbers, you'd have 0 plus 3 plus 3. All right? 0 plus 3 plus the 3 seconds, fine. Or 3 plus 3 plus 0 works just as well. So it's definitely associative for each of its elements. And also, it's got an inverse. All right? 0 goes with 0, 3 goes with 3. So it's definitely got an inverse. So that is definitely a subset, which also forms a group. So it is a subgroup of G. What about the original? Sorry, not the original. Just the identity. Now, just the identity definitely works. It's closed. It's got the identity in it because it is just the identity. All right, so it's closed. It's got the identity in it, and also it's associative. It's got to be. It's only got the identity in there, and it's got an inverse, which is of course is itself. So the subgroup, which has just got the identity in, is definitely a subset that's just got the identity in is definitely a subgroup of G. Now the last one I wouldn't expect you necessarily to spot, but the last one is the original group itself. Now the original group itself is also what we call a subgroup. Okay, the best way to think about this is if you think about factors. All right, the factors of 6. What are the factors of the number 6? Well, you've definitely got 2 times 3 makes 6, but you also have number 1, which is the identity, but you also have the number 6 itself. 6 is a factor of 6. So think of it a bit like factors. Okay, this group here is the original group, but it's also a subgroup. Okay, like the number 6 is a factor of 6. It's the number itself, but it's also a factor of 6. It's the same sort of idea with that. Okay, right, so well done if you spotted any of those 3. All right, well done. Okay, so just going back to your notebooks then, what we're going to do is just write down a bit of notation, notation we use to represent groups. Now you understand what a group is. So you take any set of numbers or set of elements, you perform a binary operation on it, and the answer you get out is a group. Right? It fulfills all the axioms, so therefore the answer is a group. Now the way we can write that is like this. And if you write it like that, you are basically saying that this is definitely a group. The set of these numbers S under this binary operation forms a group. Okay, let's look at an example then. An example could be this. All right, G is a group of all the real numbers added together. All right, so G is a group of any two real numbers added together. All right, because it's a binary operation, so it's any two real numbers. Now, just thinking about that, we could write it out a bit more mathematically. For any two numbers belonging to the set R, then A plus B belong to the group G, right, where G is a group. And just to confirm that it is a group, so the real numbers, you take any two real numbers, it doesn't matter what real numbers they are, add those together, the answer you get out will also be in the real numbers. Right? You can't add two real numbers and suddenly make a complex number. It's not possible. Okay, so any two real numbers added together will make another real number. Right, okay, so that's fine. It's closed. That means, does it contain, is it associative? Yes, addition is associative. It doesn't matter which way around you do it. All right, so addition is associative. So it's closed, it's associative. Does it contain an identity? Yes, it contains the number 0. 0's in the real numbers, and 0 is the identity under addition. Does each number in R have an inverse? In other words, any number times another number equals 0. Sorry, not times, add. So you take any number, 5, for example. Can you think of another real number that when you add to it gets you to 0? Well, yeah, minus 5. 5 plus minus 5 gets you 0. And you can pick irrational numbers. Root 2, yes, minus root 2. Root 2 plus minus root 2 gets you 0. So this definitely fulfills the 4 axioms. So therefore this is definitely a group, and that's why you could write it using that sort of notation. So look at another example. Okay, so you can put the set directly into the notation. To save you having to define what S is first, you can actually just put the set directly into here. So an example of that is this. All right, the set of just these numbers, 1i minus 1 minus I, under this binary operation, all right, so that sort of square symbol just there, that's the binary operation, that's our set. If you wanted to write the group under that binary operation, then you could write it like that. Now it's not defining what that is, it's just saying that this definitely, if it's like multiplication, for example, then it would definitely be true. It can't be addition, because 1 plus 1 is 2, and that's not in the set, but it could definitely work for something like multiplication. Okay, so it doesn't say what it is though, but they are saying that this is a group. Okay, and we can write it like that. So you don't have to just put S in there. That could save a little bit of legwork because you don't have to, you could just put the group straight in. Okay, right, take down what you need. Okay, so you just grab your notebooks then. Just put that table in and just mention the fact that it is a group of the numbers 1, 2, 3, 4, 5 under addition modulo 6. You might want to annotate this just so you're clear what this sort of notation means, just in your own notebooks, so you can annotate your own notes. And what we want to do is just formalize what we saw a minute ago. Okay, so just pause there, get down what you need before we move on. Okay, so G is a group. We can write G in this format as well. We're saying that G is equal to 0, 1, 2, 3, 4, 5. Okay, that is definitely the group of numbers. A was also a group. Right, we saw that, we proved it with the 4 axioms, that the group 0, 2 and 4 was also a group under addition modulo 6, so under the same binary operation. And we talked about this being a subgroup, we just haven't put it in our notes yet. Now A is a subgroup of G, okay, because it also forms a group. That's the important bit. We saw an example of where it doesn't always form a group. So it also forms a group, so therefore it is a subgroup under the same binary operation. Okay, so just give you an opportunity just to put that down in your notes, understanding that a subgroup must also be a group under the binary operator. Okay, we also talked about the fact that the actual original group was a subgroup. Now, if you look at any subgroups that are not the original, so not the 0, 1, 2, 3, 4, sorry, not 1, 2, 3, 4, 5, any subgroups that are not the original are called proper subgroups. So A is a subgroup of G, but it's also a proper subgroup of G because it doesn't have all of G's elements. All right, so it's proper subgroup. The only subgroup that's not a proper subgroup is the original group itself. Okay, and that's a bit headbanging, but again, think of it as factors. I talked about the factors of 6. The factors of 6 are 1, 2, 3, and 6. Now you could think of the proper factors as the 1, the 2, and the 3. The 6 is a factor, but it's not a proper factor. It's the same sort of idea as that. Any groups that are not the original are proper subgroups, or sorry, any subgroups that are not the original group are called proper subgroups. Okay, right, make sure you got that bit down in your notes as well, so you understand what a proper subgroup is. Right, so a proper subgroup B is not equal to the group G. That's a way of thinking about it. And so you could write it with this sort of notation. So B is a subset of G, but it's not equal to it. Now, if it's equal to it, it would have an extra line underneath. So a subgroup could be, if you're talking about B being a subgroup, not necessarily a proper subgroup, then you'd have B with a line underneath it is a subgroup, is a subset, or the same as G. Okay, C was a subgroup, and it was a subgroup that contained just the identity element. So it was that. Definitely a subgroup, right? It fills out all 4 axioms under addition modulo 6. Right, so it definitely works. Now, because C is the only identity element, and this would always be a subgroup, right? Because the original group must have an identity, so a subgroup could be just the identity. That's always going to be true. All right, that any group has a subgroup which is just the identity. C is a proper subgroup of G, definitely, because it's not the original group itself. Right? It doesn't have 1, 2, 3, 4, and 5 in it. But also, because it's only got the one element, and the only one that has one element like this is the identity element. It wouldn't work for anything else. People might think it's a 3 as well. Look, 3 goes to 0. All right, 3 goes to 0. But that's not a group on its own because 3 itself is not within it. Okay, so you need to be careful. So we've got C is the only element. This is what's called the trivial subgroup. So you've got a proper subgroup, which is not the original. You have the trivial subgroup. And there's only one trivial subgroup, and that is the one that contains the identity element. All right, so you take any group, it has to be a group under the 4 axioms. You could find the identity of that group, whatever the identity is, and that would form its own proper subgroup. And it would contain just the identity. And it's such an obvious basic one that they call it the trivial subgroup as well. All right, it's an obvious, easy subgroup to spot, just the identity. Okay, so we've got subgroups, but within subgroups, you have different names, proper subgroups and trivial subgroups now as well. A subgroup that does not contain, all right? So a subgroup that basically is not that first subgroup is called the non-trivial subgroup. So that could be anything. Now you could have a non-trivial proper subgroup, and that would be anything that doesn't contain these two. Okay, so in this case it would be the 0, 3 and the 0, 2, 4 groups. All right, so you could have a non-trivial proper subgroup if you put everything together. All right, so just pausing there, taking down what you need in your notebook. And I've just mentioned this, but it's worth mentioning again, that all groups have at least two subgroups, the trivial subgroup and the actual group itself. Right, sticking with your notebooks for a minute, we're just going to do a few more bits of notation. We're going to talk about the order of a group. You need to be careful because they have the order of an element later on as well. So you need to make sure you spot the difference. We're talking about the order of a group. And it's very easy to work out the order of a group because the order of a group is just the number of elements it's contained within it. So take the group 1, 2, 3, 4 under multiplication 5 that we looked at earlier on. So there it is. That's the group we looked at earlier on. The group G itself is just 1, 2, 3, 4, exactly the same as that. So what's the order of this group? It's got 1, 2, 3, 4 elements in there. So the order of that group is G equaling 4. Okay, it's straightforward as that. 4 is the number of elements within it. Don't think it's 1, 2, 3, 4, so therefore it's 4 because you're counting up to it. It's just the number of elements within the group. Okay, make sure you've got down what you need. Right, Lagrange's theorem. You need to know about Lagrange's theorem. And basically, Lagrange's theorem is talking about a relationship between the order of the original group itself and the order of its subgroups. And the theorem basically says this, that the order of the subgroup should always divide perfectly into the group itself, which goes back nicely to the idea of factors that we were talking about before. Okay, if a number is a factor, it should divide nicely into the original number itself. So the number 6 has the factors 1, 2, 3 and 6. Notice that 6 divided by any of those numbers always works. 6 divided by 1, 6, 6 divided by 2, 3, 6 divided by 3, 2, 6 divided by 6, 1. Okay, 5 wouldn't be a factor of 6 because you can't do 6 divided by 5 nicely. Right, and that's exactly what Lagrange's theorem states as well. It says for any finite group G, if you've got the order of its subgroup, it should divide perfectly into the order of the original group itself. And this is a nice way to spot whether a subgroup works or doesn't. Okay, we could have spotted earlier on that 0, 1, 2, 3, 4 didn't fit within 0, 1, 2, 3, 4, 5, 6 because it was not going to be dividing into it nicely. Okay, we showed it a different way. We showed it failed an axiom, but you can show it using Lagrange's theorem. So let's have a look at an example. Determine the possible order of the subgroups of groups of order 50. So I've got a group that's got 50 elements in it. So clearly I'm not going to write that down because I'm not going to have 50 different elements. So I've got 50 elements within my group. But what is the possible order of the subgroups of that group? Okay. So the possible subgroups, there should be a subgroup potentially of order 1. That's going to be the trivial subgroup. There should be a subgroup with 50, all right, depending on whatever the binary operation is. There should be one with 2, one with 5, one with 10, one with 25, and one with 50. Notice we're basically just looking at the factors of 50. 50 being the original subgroup itself, the original group. Okay, and that's all Lagrange's theorem states. Now you can have the examiner asking this in the opposite direction. It could be a situation where they say, look, we've got a subgroup which has got an order of 30 of the original group 50, and you can say that's definitely not true because 30 doesn't go into 50, doesn't divide nicely into 50, so therefore it is wrong that the subgroup of 30 is of the group with 50 elements. So you have to be able to understand it backwards as well. Okay, still sticking with Irby language. X is the element of a group. So X is just some number within the group. All right, just any of the numbers within this group. So when you do the set S under the binary operation, circle with a cross, it produces some number. We'll call that X. Okay. Xn means you apply that binary operation a certain amount of times. So say this binary operation is addition. All right. I could take a number in the group, right, any number in the group, I could add it to itself, and that would be x squared. Because I'm taking the x value, I'm taking the number itself, and I'm doing the binary operation on itself. So if a binary operation, say for example, was addition, and I wanted number 5 to be my element, then 5 plus 5 would be 10. I could do it again, make it 3 times. 5 plus 5 is 10, plus another 5 is 15. That would be x cubed. X to the power 4 would be adding another one, and so on. And this is what this says. X to the n, x to the power n, means applying that binary operation on the element repeated number of times. Now that sort of fits in our understanding of powers, because when we think about powers, we think about multiplying by itself a certain amount of times. Now we're applying it to binary operations, so it's not just multiplying, it means that binary operation could happen any amount of times. Okay? So one I've just mentioned, x squared would be x binary operation x. Right? X to the power 3 could be x binary operation. Get a result from that and then do the binary operation again. And so on. So x to the power 4 means do the binary operation and then again and then again. It's a bit like a composite function. It keeps working out the inside bit. All right. Okay, so have an investigation on this then. So I've got the group G, which is all the numbers from 0 to 7 under modulo 8. And what I'd like you to do is figure out x to the power 1, x to the power 2, 3, 4, 5, 6, 7, and then finally start with it, ending where you started, x to the power 8. Okay, so all I'd like you to do is just write the sequence you get. So the first one will be the number itself. So x to 1 is just whatever the x is, 0. X squared would be 0, it's addition, plus 0. So 0 plus 0 is 0. Okay, x to the 3 would be x squared plus another 0. So that would be 0 plus 0, 0 plus another 0, 0, and so on. So this is a very boring sequence just here. Okay, what I'd like you to do is see if you can figure out the rest. Don't be lazy. Pause it there. See if you can figure out the rest and see what you spot. Okay, so hopefully on this one, you said, well, the first number, x1, is just 1. So that's going to be the number 1. Then you've got x squared. So that's going to be 1 plus 1 is 2. X cubed will be 1 plus 1 is 2, plus another 1 is 3. So this is a nice simple sequence. 1, 2, 3, 4, 5, 6, 7, 0. 2, slightly more interesting. 2 plus 2 is 4, so it's 2 then 4, plus another 2 is 6, okay, plus another 2 is 8, but don't forget we are modulo 8, so I don't want to see any numbers that are 8 or bigger, so that goes back to 0. Then you've got 0 plus 2 is going to be 2, 2 plus 2 is 4, and so on. So what you notice is you get this repeating pattern just here, 2, 4, 6, 0, 2, 4, 6, 0. Number 3, 3, 6, 9, is going to go back to 1. All right, 1 plus 3 is going to be 4, and so on. So you get this sort of pattern, but you always end up with 0. Okay, that's just to do with the fact it's on modulo 8, but it's quite nice to see you get this repeated pattern. Number 4, all right, 4 is very interesting because you've got 4, then 4 plus 4 is 0, then plus 4 is 4, then plus 4 is 0, and so on. 5, 10, but that's 2, plus another 5 is going to get you 7. So we do get this pattern, but it ends up at 0 in the end. And every number gets generated out. Number 6, 6 plus 2 is 4, because it's 8, because it's 12. 4 plus 6 is 10, but that's going to be 2. 2 plus 6 is 8, so that's going to be 0. So you end up back at 0 within four goes, and then you repeat again. No odd numbers in sight. Number 7 sort of works down. So 7, 6, 5, 4, 3, 2, 1, 0. All right, so you're getting all these different patterns out by using just a single element from the group. So I've used every single element, and what I've noticed that each of them produce their own different sequence of results. What do the sequences have in common? What would you say is special about each of the sequences? Knowing what you know about geometric sequences, things like that, arithmetic sequences, what could you tell me about each of those sequences? Now, if you said the word periodic, you'd be right. Okay, they are all examples of periodic sequences. They have this repeated pattern. All right, even if I carried on going, this is going to count with zeros. This will go back to 1 and start the sequence all over again. So they're all periodic. Now, if they are periodic, they should have a period. what I'd like you to do is just go down and just write the period of each of those sequences. And so the period is how long it takes before it starts to repeat. Okay, so just pause there, fill them all in for me. Okay, so the first one repeats straight away, doesn't it? So that period is literally just 1. Within one number, you're back to where you started. This one, though, doesn't get back to where it starts until the 8th number. So that's a period 8. This one, number 2, 2, 4, 6, the 4th number along is where it repeats itself. So it's period 4. And so you can go down 4, 8. This one's every 2. This one's 8 again. Oh, this one's every 4th one. And this one here is every 8th. So we get the period of each of those elements. All right, so we've got the period of each of those elements if it was looking at it as a sequence. Now the lowest value of n for each of these such that it gets back to the identity element. So how long did it actually take from the identity element itself? All right, starting from the starting number, how long did it actually take before you got back to the identity, which is 0 in each of these cases? All right, just have a look down that list and just think about how long did it actually take to get back to where you started. And there's no surprises for noticing that you actually get back to the identity element exactly the same answer as the period. All right, x to the power of the period is the very first one that gets you back. X to the 8 was the first one that got back. X to the 4 was equal to the identity there. So how long it takes for the sequence to get back to where it starts is exactly the same as the n value. Okay, so we've done that investigation. Let's just formalise this in our notebooks. So x is an element in the group S, whatever your binary operation is. The period of the element, sometimes called the order of the elements, not the order of the group. All right, you need to understand both bits of language. We're going to call it the period so we don't get confused. All right, between the two things. So the period of the element is the lowest value of the n for which this is equal to the identity. All right, so it links in with the period to do with the sequences. So it's how long do we have to go before we get back to the identity. So once you know what the binary operation is, then you could figure that out yourself. All right, you could keep going until you get back to the identity. And this only works for sequences like we just saw, which sort of cycle back round. I've mentioned this, and it is worth putting down your notes. The period of the element is also called the order of the element. There's an order of the group, which is how many elements you've got in it, and you've got an order of the element. And the order of the element is how long it takes to get to the identity if you keep repeatedly adding or doing the binary operation. So let's have a quick look at this. So the period of the element 4 in the group 1, 2, 3, 4, 5, 6, modulo, set a multiplication under modulo 7. Okay, so grab your notebooks, make sure you've got this down, and you might want to have a go at yourself. Okay, so I start with the number 4. Clearly that's not the identity. I need to know what the identity is. So I know what the identity is. The identity is going to be 1. So I start with the number 4. 4 is not the same as 1, so it's not going to be x to the 1. So then I investigate x squared. So x squared is 4 times 4 is going to be 16, but under modulo 7, that goes back to 2. That's not the identity. I'm going to have to try the next one along. 4 to the power 3, so that's 4 squared, which was 2, times by another 4, which is 8. So then that's going to go back to x to the power 7. That to me is the identity. All right, number 1 is the identity. So therefore I can stop just there. The period of the number 4 in this group is 3. All right, it literally took 3 goes to get to the identity. All right, so just write down what you need in your notebook. So most of the groups we've looked at so far have been what are called finite groups, but you can also get infinite groups. The real numbers here form an infinite set. So the infinite set of real numbers under the binary operation of multiplication will form an infinite group. All right, so just give you a moment in your notebooks to write that first bit of notes down. There's absolutely nothing wrong with infinite groups. They still follow the 4 axioms and therefore could still form a group, exactly like this one can just here. It's also worth noting in your notebooks as well the fact that most of the ones we've been looking at are what are called finite groups, where the actual set itself is just a finite number of elements. So an example of that could be something like this, where you are just putting in numbers 1, 2, 3 and 4. So it's a finite number of elements, so that will be referred to as a finite group. You need to understand about both finite groups and infinite groups. Okay, so let's put this question down in your notebooks then. We want to show that the group of all the real numbers under the binary operation of addition is a proper subgroup of all the complex numbers under the binary operation of addition. And it might seem quite obvious, but we need to learn how to actually go about forming an argument to show that this is going to be a proper subgroup of this. Okay, so get the question down and let's just have a work through the answer. Right, so some of it is already stated the fact that these two are groups. So we're not trying to prove that these two are groups. What we need to do is just think about the arguments to show that this is going to be a subgroup. Forget the word proper for a minute, a subgroup of this. Well, if it is a subgroup, they must contain the same identity element. All right, that's important. So the identity element of this group here is exactly the same as this group here. Now we know even for the complex numbers, all right, under the binary operation of addition, the identity element is going to be 0. Is that contained within this group here? Yes, it is. It is contained within that group, right? Is in that group, and also it is the identity element of that group as well. All right, so the identity element is 0 and it is contained within both group and subgroup. Okay, and that's important. That's the first part of an argument that you could have. Then you can start looking at some of the numbers themselves. So if you take any real number and you add it to any other real number, then we know that the answer is going to be a real number. We know that, and it's also stated up here that it's part of the group. And it's also true that for any number, it has an inverse, which is minus x, which also belongs to the real numbers. Now we're showing that really this is a group. But what's important is that for any of these answers that are real, they're always a subset of the complex. So as R is a subset of the complex numbers, and the group R plus is definitely going to be a subgroup of the complex numbers with a binary operation of plus. Right? Because that is a subset of that, and they're both groups, then that is definitely going to be a subgroup of that. Okay, so it's just trying to state this point and making sure that you're showing that R is definitely a subset of the complex numbers. Don't forget, you could have two groups that are subgroups of some bigger group, but not necessarily subgroups of each other. So you need to be careful. It's not always the case that they're going to be subgroups of each other. All right, but in this case, it definitely is. Then what? Well, we need to also show that it's a proper subgroup. Now, the way we can show it's a proper subgroup is by just picking any element that's true in here that's not true in here. Okay, so the obvious one for the complex numbers is going to be the letter I, or the number I. Now, I definitely belongs to the complex numbers under addition. But because it's an imaginary number, it doesn't belong to the real numbers at all. So I belongs to this group here, but I does not belong to this group. So therefore, this group has less elements. It is still a subgroup, but it has less elements. So therefore, it is not the group itself. So it is a proper subgroup. Okay, but it's just a case of just trying to get as many arguments as you can, making sure you're really showing the examiner that you understand about the axioms, that you understand about the identity element, and understanding about the fact it's a subset means that it's going to be a subgroup if they're both groups themselves. Okay, so just try to tick off quite a few little arguments before you make the statement at the end. Okay, sticking with your notebooks again, we're going to look at a different question, a bit bigger this time. So I've got the Cayley table. I've got the elements A, B, C, and D. This is the results we get under the binary operation with the triangle. So I'm going to pause there, give you an opportunity to write it all down, or write down what you need, including the Cayley table, and then we'll have a look at each of the questions A through to D. Okay, so question A then is saying, can we prove the set A forms a group? All right, so we need to actually show that this actually is going to form a group. We need to figure it out. Under the binary operation, triangle, given that triangle is commutative. All right, so we're going to come back to that idea in a minute. We haven't come across commutative recently, so we're going to talk about why that helps us. Okay, so if I want to show that it's a group, I've got to fulfill the 4 axioms. Now, just because it's letters, all right, for the elements rather than numbers, doesn't mean we shouldn't be able to figure this bit out. So the first thing we need to do is just have a look and see whether there's an identity in here. Okay, or just do this when it's closed. Notice that all the outcomes here, A, B, C, and D, all right, are all in here. There's nothing different in here that wasn't in the original set. We've got A, B, C, and D appearing. Nothing else new. So therefore, whatever elements I pick here, and I do the binary operation triangle to it, the answer I get is always in the original set. So therefore, it is definitely closed. All right, so all possible outcomes are definitely within the group G. All right, because we're trying to show that it forms a group G. All right, so I've shown it's closed. Let's go back to the associative. Now to show it's associative then, I need to show, and this one's going to be a little bit longer, I need to show that A, B, C, so A and then B, and then C on it, is the same as doing B and C and then A on that. I need to show that it's associative. So let me just do that. A, B, and then C. Well, A and B, so A, B is like this. Notice it's commutative, so it doesn't really matter which way around I read the table. But with binary operations, it's always this one first, this side first. So it's A, and then B is B. So I can change that to B. B then C is the same as D. So I can say that's the same as D. Now, if I spot where a D is, remember I'm trying to get back to this answer just here. So ideally, I want to show that this is the same as BC. And if I look, it is the same as BC. So I could definitely say that's the same as AD. All right, so AD is the same as that. And I know that D is the same as BC. So therefore, I can write it like that. Okay, I can also do the same for AC. So I'm going to have to go through each of them. That's probably worth you just pausing here and having a go in yourself and make sure you can show them all. Okay, so AC is C. CD is going to be A. But then, if I want A, that is exactly the same as AA. All right, that's the same as that one. And then I know that A is exactly the same as CD. So therefore, I'm showing that that is the same as that. And then finally, this is going to be the same as DD. DD is the same as B. B is the same as AB, or BA, whichever way I want to write it. I can write it whichever I like, but remember I'm trying to engineer this situation with the B at the front. And CD, well, A is the same as CD. So I'm sort of engineering this the other way around and just making sure that it is actually true as I go through that rigorous argument. And I'm showing that it's associative. Now, because it's commutative, it doesn't matter which way around I put these things. It should always be true. All right, so because it works for those 3 there with all the possible combinations, therefore it's definitely true for all of them. All right, and that's why the word commutative was important. So it saved you having to do all the things like B, A, C, and things like that. So therefore, it ticks off the associative bit. The G group is associative, yes. Right, the identity for it is going to be the one that doesn't change. So look, AA is A, AB is B, AC. So therefore A is the identity. Works the same. You're looking for the columns and the rows which are the same as the original set. And then the last bit is the inverse. So everything should have an inverse, right? That goes back to A. And as you look through, A goes with A, definitely back to A. B goes with B, so that's a self-inverse. That one's fine. B goes with B, they're self-inverse. C goes with D, and D goes with C to get you back to A. So they all have an inverse. And because they all have an inverse, therefore, There we go. B goes with B, C goes to D with A, and D goes to C with A. So therefore, they all have an inverse. So you could argue the fact that set A forms a group under the binary operation triangle. And that's the answer to question A done. So answer to part B. So part B, just asking us to state the order of the group. So the only bit of advice I'd say here is just make sure that you are looking at the order of the group and not an order of an element. They are slightly different. You can see that at the bottom when it's asking for the period of each element. So they could sometimes ask you the order of each element, but they're asking for the order of the group. Now in this case, the group, which we've figured out that A is a group. So the group G is A, B, C, D. There are 4 elements in that group, so the order of the group is just the number of elements. So the answer to part B is just 4. So let's look at question C. Identify all subgroups of the group. So now that we know that the order of the group is 4, okay, so the order of this group is 4, that means the possible subgroups can only have an order which is a factor of 4 that go into 4. So it could be 4, which it would be, the actual group itself. It could have an order 2, all right, so you could have ones that have got an order 2, or it could have 1, which will be the group that contains just the identity, so the trivial subgroup. So we need to go through and just make sure that we're aware of the order of the subgroups, and that would help us figure out what these subgroups actually are. So the ones I'll definitely write down will be the actual group itself. So we've definitely got the original group, and that also is a subgroup. But apart from that, the other options would be ones that can only contain the same letters. So for example, if I look at the AB and AB, the answers that's contained within there will be A and B. So therefore I know straight away that that's going to be closed. C and D, for example, contains exactly the same. But the problem with that is that C and D produce the elements A and B, and A and B are not within that subgroup. So the only ones I'm really looking for are ones that contain the same letters. If I try A, B, and C, I know that's wrong anyway because that has an order 3. All right, and you can also see that's going to produce D, so that's no good. A and C, oh, that produces a B, so I can't pick A and C. And A and D, A, D, D, oh, B, so that's messed that up. If that was an A, that would be okay. So what I'm looking for is anything that can actually work as a subgroup with an order 2. It has to contain A because A is the identity. So it's no good trying to miss out A. So I know AB works, AC doesn't, and AD doesn't. So the only other subgroup I would say that works is this subgroup just here, which has got AB. And I could check that. I can see it's got an inverse. I can see it's closed. It's only got A and B, so therefore I know it's going to be associative because the previous group was associative. And of course, A, B gets you back to B, so therefore there is an inverse for everything. And B, B gets you back to A. So therefore the inverse of B is also B. So I've got that as a subgroup. Notice the order 2 is a factor of 4, so I agree it's going to be right. And the other group we could actually have will be this group just here. All right, the trivial subgroup. So that's a proper subgroup there. These two will be the proper subgroups. That one there is the trivial subgroup. It's not asking for that, but it's worth you making sure you're aware of it. And the first one was just the original group. Okay, question D then. So for question D, we need to be looking at the period of each of the elements. So what I'm going to do is starting with A first of all, and I'm going to look at A on its own. That's x1. All right, so I'm looking at x1 equaling A. And also once I've done that, I want to see how many times I have to keep using the binary operation on the element until I get back to A. That's what I'm looking for. Okay, so starting with A. A definitely has order 1. It's the identity element. It's always going to have order 1 because it produces all the others. So A on its own is just A. So that's one done. What about B? Well, B with B goes back to A straight away. Okay, now B on its own is B. B squared, so B with the power 2 is that. So therefore it's going to have order 2. So if I looked at the pattern of B, it would be B, A, B, A, B, A, and so on. It has order 2 because it's got a period of 2. C, if I try that, so C with C first of all is going to get me to B. Once I've done that, I can go with C again. Remember, you're going with the C value each time. It's all about the binary operation with C. So this one here is C with C and then C again. Now that's going to go C with C is B, B with C is to D. Then I need to go D with C. Now D with C is going to go to A, so therefore it's got order 1, 2, 3, 4. I had to do it 4 times. Okay, 2 times to produce B, 3rd time to produce D, 4th time to get back to A again. So order 4. Finally, D. Now D with D is going to be B. Then I can go to B. B with D is going to be C. Then I go to C. Now C with D is going to go to A. And so therefore I've got 1, 2, 3, 4. Therefore D has order 4. Okay, so we've managed to go through each of the elements and work out the order of each of the elements, or what's called the period of each element. So there's a couple of exercises on page 111, exercise 7.2 for you to have a go at.